So thank you very much for the very kind introduction. It's my pleasure to, come up with a slight change of subject, and I realize this is very much different in the sense that it's typically not a sample we're using. I'd also like to mention that I used material from quite a number of colleagues, which are all familiar to you, many of you. So thank them, even if they might not know that I used their material today. Let's first start with a quick look at the standard model. So when we look at particle physics, then we think about particle, what does our model of particles actually describe? And we know that the particle content, which you can see on the right, of the standard model nicely describes practically all the experiments we see in experiments at high energies, at low energies, in astrophysics, anything. And this is somewhat puzzling because it also fails to describe certain things. So if you look at the interactions, we know that there's the electromagnetism in there. Described by the photon. We know that there's a strong interaction in there which holds the nucleus together, described by gluons. And then there's beta decay, etc., described by the weak interaction with the Z and W bosons. And of course, there's the Higgs, which gives particles mass. But there's something in there which is not described really, right? We have no idea how gravity or general relativity really fits in there. We know from cosmological observation, astrophysical observations, that there must be something called dark matter or dark energy. And there's no candidate in the standard model which might explain that. It's also pretty embarrassing that our standard model does not give reasoning why we even exist, because it cannot describe the dominance of matter over antimatter in the universe. So this is a mixed ingredient. It also does not tell us if there's something called the unification of forces or where the neutrino mixing comes from, etc., etc. So if you want to find out about those things, then you have basically three strategies. You can either go to colliders and try to directly produce new particles. This is called the high energy frontier. Or you can look at astrophysics observations, which is called the cosmic frontier. Or you can do precision physics at much lower energies. Forgive me this cartoonish way of looking at it. If you look at the high energy frontier, what you're really trying to do is like what you've done here for the Higgs, in the sense that you do gluon fusion and you produce a new particle, which you see then as a resonance. And this is can be described as looking for dinosaurs, like heavy new particles. The other way of doing it is, and this is an electric dipole moment chamber, is going to very low energy measurements with highest precision, where the standard model background is really small, and then you look for teeny tiny deviations from your expectation. And you can think of this as looking for footprints. So heavy new physics, new particles imposing slight changes, footprints on low energy physics. And I'd like to give you a little bit more of a hint how you can understand this, how this can even be competitive. So let's just assume that we have you look at this Feynman diagram. So this is like a scattering event, but does not have to be, where you interchange a new heavy particle. You would describe this by coupling constants here and there, and then you would have the propagator term here, which goes 1 over the momentum transfer squared minus the mass squared, which means that if this new particle is really heavy, the momentum transfer does not really play any role, and your propagator term is really proportional to 1 over m squared. That actually means that it doesn't really matter at which system you're looking at, what kind of momentum transfer you're creating. You have to make sure that you're able to measure this contribution 1 over m squared. And that means you have to go to a system where measurement precision is really, really high, and the number of particles are abundant. And well, for us, very often the neutron is at the sweet spot where the number statistics, the number of neutrons match, and the measurement precision is very high because it's such a nice particle. So if you now look at where can you do particle physics with neutrons, then there's traditionally a lot of strong instruments at ILL in Grenoble, which we'll look at in a second. But you can also go to PSI, where they have ultra-cold neutrons and, well, a general purpose cold beamline, and the particle physics beamlines and instruments at the EFREM in Garching are still under construction. And well, if you would like to know about potential new endeavors at the European Spallation Source in the that just has been last week a event at ESS discussing the options there. So let me first classify those instruments a little bit. These fall under cold neutrons, which with the dominant player here being the PF1b beamline, which is a polarized cold neutron beam facility. And then there's ultra cold neutrons, which you learned about earlier on in this session. And I tell you a little bit more about those. And you see that there's a number of sources at different places now, and some just starting operation at very high intensity, SuperSun, some of them being the flagship experiment for decades, PF2 at ILL, and some serving special instrumentation at PSI, for example, for the EDM measurement. But there's also smaller sources, for example, at this Trigger reactor in Mainz, which is a prototype source for the FREM2 source, which is still under construction. And then there's specialized instruments for nuclear physics, like the fission separator, Lohengrin, or the fission product gamma spectrometer, FIPS at ILL, or even interferometer S18 at ILL. So let's go through those categories and see what kind of applications they have. One thing is that in many cases, not all of them, particle physics are a little bit different in the sense that we don't bring samples to the instrument, but we bring large-scale experiments, large setups to the experiments. And this one is one of 2 trucks of the Perkeo 3 experiment, which was installed temporarily at ILL 4 times now, which means moving 2 trucks of material for a certain period of time to ILL, installing everything there, and taking things down again after, depending on the beam time, 3 to, let's say, 15 months or something with Perkeo. So duration of those experiments is also just like the preparation of those experiments, typically years. And so running time is between weeks and many years. And if we now have a look at the destination of this experiment, this would be PF1b at ILL. And as you can see from the sketch, there's a cold neutron beam being delivered. There's a casemet with polarizer and options for velocity selector, etc. And then there's the experimental zone. And in the experiment zone, you see exactly nothing really, because this is how it looks like when there's already something built up, namely part of the beamline. It's basically an empty pit. So it gives you much flexibility in installing your own precision experiment and providing the necessary surrounding. And if you look at the beam itself, for example, this is enormous, right? This has a cross section of 6 times 20 centimeter and a total flux of on the order of 10 to the 12 neutrons per second. With a density of 2 times 10 to the 10 neutrons per second and square centimeter. So this is highest flux possible in terms of cold neutrons and very flexible place to set up instruments. And this slide shows you several options of what this beam site has been used in the past. And you see that in the middle, this is the PHotons instrument, which you've just seen on the part of on the picture on the truck. It basically fills out the pit. There's vertical magnet like the aspect beta decay spectrometer. There is the Brand instrument, which also fills up most of the space there. And one of the newest installations there was the Beam EDM by the group of Florian Pixar and colleagues, trying to revive the with a new technique, beam electric dipole moments measurements of the beam. Those would be EDM measurements and beta decay measurements of the neutron, where you look at the actual neutron decaying, and EDMs I'll explain in a second. But there's also large-scale nuclear experiments where you look at, for example, within the Exile campaign, you look at neutron capture in selected nuclei, and you observe gamma radiation in coincidence in multiple detectors surrounding those. And this was a gamma ball transferred from Ganil, for example, right? Multi-million installation. So as a first example, I'd like to tell you about beta decay, of course, because that's what we are doing. Basically what we're doing with PHotons is we're looking at the beta decay of the neutron, where if the neutron decay into an electron, a neutrino, and a proton. And you might remember that the angular distribution of those electrons stemming from this decay is not isotropical, but it rather follows this cosine 1 plus cosine theta distribution, where the capital A here is the so-called beta symmetry parameter. And this tells you basically that the weak interaction distinguishes between left and right. So this was big news in 1957, where it also rightfully obtained, yielded the Nobel Prize for the discovery with cobalt-60 by Wu et al. But nowadays we're still performing this with the highest precision with PHotons. And the method we're doing this is pretty simple. You have those neutrons in a beam, polarized, highly polarized, with up to 99.7%. And then you look at the decay, and the electrons are transported to 2 detectors on both sides. And they gyrate around the magnetic field lines because the energy is just 1 MeV maximum. And this basically lets you integrate this cosine theta here over a hemisphere, which means this cosine theta is integrated a half. And then you get this experimental asymmetry by just comparing the number of electrons at a given energy emitted in spin direction or and against spin direction. And this is our observable, a very simple measurement. Of course, there's a lot of systematic pitfalls, but it's very easily explained. And then you can see the asymmetry in the signal straight away in spin up and spin down, and the experimental asymmetry is then our observable. And this is a 10 to minus 4 measurement with the largest data set obtained there by an order of magnitude or so. So why is this interesting and becomes even more interesting lately? This is due to, well, of course, this is input in general because the neutron decay is a typical beta decay, and the correlation and the coupling constants from this decay are needed in a lot of calculations, being energy production in the sun or the number of light elements in the early universe, um, or for example, the calibration of neutrino detectors. But the other thing is that we're really looking for new physics. And one thing is that the eigenstates of the weak interaction and the so-called mass eigenstates are not identical, but they're transformed by the so-called Kabibo-Kobayashi-Maskawa quark mixing matrix. And since you have the transition of up to down quarks in neutron decay, you're sensitive to this element. And our colleagues at the colliders, they do this CCAM unitarity triangle, which is one of the most stringent tests of the weak interaction and the standard model. But you can also do just as precise test by squaring the first row, because this, of course, being a rotational matrix, being a unitary matrix, has to be equal to 1. And it turns out experimentally it isn't. So this might hint to new physics in the sense that the matrix is incomplete. And it actually tests at this level of precision, tests for new physics at the 10 TeV level. Neutrons can contribute there. At the moment, this measurement is from nuclear decays, but the most precise way in the future might be from neutrons by just a factor of 2 improvement. And one thing we like to do there is with a measurement that at FRM MLZ with a new beamline, which is about as powerful as the PF1B beamline, which will host the successor to this instrument called PALC, depicted here on the right. And you can see here the red stones are the recent progress in installation there. So it's should be ready when the FRM restarts next year or so. So let's switch gears and go to ultra-cold neutrons. Ultra-cold neutrons are special in the sense that you can actually store them in a bottle and carry them around. Because a layman's definition of ultra-cold neutrons is that those are neutrons who reflect from any surface, from a given surface under any angle. This means you can store them, and here on the right is a picture of a magnetogravitational trap, sorry for the typo, of the UC and Tau experiment in the US. But what you can see here is that the magnetic potential by this magnetic gradient field is 60 nano eV per Tesla. The energy loss per meter is on the order of 100 nano eV, and the wall interaction is on the order also of 100 nano eV, the Fermi potential, being gravity, magnetic field, and strong interaction combined, and you can use all of them to store ultra-cold neutrons, which means that the benefit of using those neutrons is that you have a system which you can store in place and observe for a very long time. The drawback is ultra-cold neutrons are a very scarce species. They're hard to come by. And the reason being is basically you have to extract them from your cold spectrum, which only has a very tiny fraction at those low energies of 100 nano eV or below. So the leading instrument in the field, in many aspects for decades, it's been the ultra-cold neutron source PF2 at ILL at NEPHEWS. And here you can see the spectrum. It's really a source which serves 4 beam ports, and you can see the spectrum has a maximum at around 8 meters per second and extends to 15, 20 meters per second, something like this. And the way it works is that you extract neutrons from the cold source vertically, and you climb up where they lose energy already, and then they hit this turbine, and you see the blades, and the blades are like a footballer stops the football by moving along with the ball. The foot along with the ball, it stops the ultra cold neutron, the neutrons, and puts them into the ultra cold regime. The nice thing about this is it's been running steadily ever since its installation, very highly reliable, and it offers a continuous beam in contrast to modern other sources. This looks like this. So here you can see the guide going up to the turbine, and the turbine is in this vacuum vessel. And this then serves experiments which sit on these platforms. And if I'm not mistaken, this might be Tobias Jenke as the beamline responsible there. Of course, this has been used to measure electric dipole moments, the neutron's lifetime, and a lot of other things in the past decades. But the experiment I'd like to show you now is something you can do, which is kind of textbook physics in a sense. So quantum mechanics 1, you store gravitationally neutrons above a mirror. So you use the potential of the gravitational field, mgz, and in this case, you also have an absorber above, and then the solution to this linear potential is Airy functions. And the interesting thing is that the energy scale of those levels is pico-electron volts. Realize the another orders of magnitude in energy below. And these, so the ground state is at 1.4 pico-electron volts. And unlike a harmonic oscillator or your double wall potential, the spacing between those is always different. So what you can do is by exciting transitions between those two between those levels, you can perform spectroscopy just like you would on any quantum mechanical system, which is an interesting idea. Why should you want to do this? Of course, if you have interaction at short length scales, new interactions, let's say you have additional extra dimensions or additional, for example, chameleon fields, then those would shift those energy levels slightly, which you could then see in your spectroscopy measurement. And one of the most precise measurements to do this kind of things is to use Ramsey's method, which is also used for EDMs, and explained later on. But this is the experiment Q-bounds at the PF2 beam site. And what they're doing here is they have this selection of states. So they have this mirror and the neutrons, and you see the wave function squared depicted here in colors of the neutrons above the mirror, and you select a few states of those by absorbing them, limiting the number of states which can go through the slit, and then you have a transition stage. In this case, you just vibrate the lower mirror, which then would induce transitions to higher states, which you can see here. And then you let those states propagate, and you have a second transition state and a selection or analysis stage. And here you can see a picture of this. The two curves indicate resonance curves for different phase shifts between the transition region 1 and 4. 2 and 4, sorry, and you can clearly see how they drive transitions 1 to 6 or 2 to 7, respectively, driving those back and forth. And by measuring the exact oscillation frequencies, you can then test for additional interactions on the path from your first transition to the last transition. Our colleagues at PSI have built another ultra-cold neutron source. This is now driven directly by a proton beam, where you have a spallation target, a heavy water moderator, which converts them to thermal neutrons, and they're now converted to ultra-cold neutrons in something called the super thermal process, which is basically scattering on phonons and protons in the medium, which scatters them down. I'll show later how this works for helium, which is easier to see. And also here they serve different instruments, namely the NEDM or its successor N2EDM, neutron lifetime experiment, and they also have a test port. So I think I'll skip this one. You see here that the spectrum from this is slightly softer, so you have a maximum at around 5 meters per second, depending on the time after storage, and they use this mainly for using the electric dipole moment. So why would have a neutron have an electric dipole moment, you might ask? Naturally, it doesn't. It has a spin, it has a magnetic moment. So let's just assume it has a slight displacement on average of the negative and positive charge. It's made out of quarks, so maybe on average those have a slight separation between each other, and this might cause a magnetic moment. If you look at the time reversal process, then the magnetic moment would change the direction, but the dipole moment along the same way would not. So this is a time reversal violating process, and actually Ramsey and Purcell looked at it to find parity violation, which was ultimately found in beta decays. But since it's violating time, it also by assuming CPT, meaning charge conjugation parity and time reversal conservation, it violates CP. And CP searches or CP violating searches are all over the place. They're very heavily much sought after, in the sense that earlier already alluded to that we don't understand why there's this amount of matter-antimatter asymmetry in the universe. And the reason being that there's too little CP violation in the standard model. And if you turn that argument around, the very tight limits on EDMs put very, very stringent limits on any new physics model a theorist might come up with, because the standard model expectation is practically zero. Just let me mention briefly that, of course, I think since these are footsteps, you don't know what you're actually looking at. But if you combine signals from, let's say, the neutron and mercury or ytterbium fluoride, all electric dipole moment measurements, you can rule out something like the MSSM supersymmetry model to very high predictive power already before you can do this at colliders. So how is this done? This is again the same kind of Ramsey principle you've seen before. You prepare your states in the sense that you polarize the neutrons, then you flip the spin and let them Lama precess in a field and over a certain time or distance, depending on what you do. And then you apply a second in-phase pi half pulse to restore polarization. And by applying an electric field in opposite or parallel direction to the magnetic field, if there would be a dipole moment, then you would shift the frequency. And if you look at the difference of those two frequencies in both directions, then you're highly sensitive to this electric dipole moment. You're also highly sensitive to the remaining magnetic field, which is why electric dipole moment measurements have to be very, very thoughtful about magnetic fields. Unfortunately, the sensitivity only goes with the square root of n, which means for better measurement, you need much more neutrons. And this is what is done. It has been done at PSI. So you store the ultra-cold neutrons now between those two electrodes. You apply a high electric field and let the neutrons do the Ramsey cycle in here, and then they obtain, after years of measurement, a electric dipole moment which is compatible with 0, with a limit of 10 to minus 26 statistically and 2 times 10 to minus 27 systematically. The statistics is limited by the number of neutrons, and the systematics by how well you can shield magnetic fields, how uniform you can make the magnetic field inside. Also at ILL, they built a new source to improve electric dipole moment measurements, and here they use not solid deuterium but liquid helium as a source, and this is the phonon-roton dispersion curve of superfluid helium and the dispersion curve of free neutrons. And if you now have neutrons hitting liquid helium at the right energy at a wavelength of around 8.9 angstroms, they will be downscattered by scattering on a phonon. Of course, this has to be in detailed balance. It's a thermal process, so this requires very low temperatures in the liquid helium, ideally much below 0.8 Kelvin. And indeed, colleagues realized this, and this is now working, and it's delivering now something like 4 UCNs per cubic centimeter to the pan-EDM electric dipole moment measurement installed there, or will deliver, which is about a factor of 4 more than what could have been done at the PF2 beam site. Let me just briefly also tell you that it also accumulates, so it accumulates UCNs in the source vessel for a certain amount of time, in this case 1500 seconds, and then the beam is switched off, and only then you can release the ultra-cold neutrons into the vessel. This is how it's done here. So it's an accumulation and emptying, so it's a spill of ultra-cold neutrons coming out. So clearly this source is well suited to the EDM apparatus, and probably also a lifetime measurement, but for the Q-bounce experiment, this would be challenging because they need a continuous beam. And I think I'm kind of running out of time. So let me briefly skip over the nuclear instrumentation. FIPS is basically an evolution of the Exile campaign because it was so highly successful. We can use the neutron as something, doing something with your sample, in that case, causing fission or gamma radiation, and you detect those by gamma balls. There's the low and green instrument, where you have irradiate samples in the reactor, uranium, plutonium, etc., and collect fission samples, and you look at conversion electrons or gamma rays and beta decays of those fission fragments. And last but not least, very diverse, there's also interferometry, where you have a Mach 10 interferometer built for neutrons, produced out of a single piece of silicon. Colleagues are working on having this produced from multiple pieces, but the precision right now requires that you have those parallel at a molecular atomic level. And so you have 2 paths which you can bring into interference. and use for experiments. I leave it at this. Hartmut describes this on this website very nicely. Okay, so for those who are still there, thank you much for staying there until the end. I hope I could give you a glimpse on things you can do with cold and ultra cold neutrons in terms of particle physics. And let me briefly just remind you that it's really competitive in the sense that it looks for new physics at the 10 TeV to 100 plus TeV level, mass level. Much higher than what you can produce directly at any collider. Um, um, if you perform such experiments, then of course I highly recommend you contact your beamline scientists early, because there are certain technical and safety aspects which you have to take into account. And I also appreciate that ILL implemented a new beam time access scheme for these kind of proposals, named extensive beam time access. So thanks for staying along, and I'm happy to answer any questions.